Spark GraphX and Graph Analytics. Preface. Content of this lecture. In this lecture, we will discuss GraphX, a distributed graph computation framework that unifies graph parallel and data parallel computation for big data analytics, and also discuss in this lecture a case study of a graph analytics with GraphX. Here on the bottom right, we have shown the position of GraphX, which is above the Spark, Apache Spark core. We are going to discuss this component, that is the GraphX, which is a part of core Spark in this discussion. Introduction. So, a piece of technology which is built on top of the Spark core we are going to discuss, that is called GraphX. Now, graphs are like our social network graphs, which are very well known in computer science and in the complex networks. However, the graphs are only useful for specific things. For example, it can measure the things like connectedness within a particular domain, the degree distribution, average path length, triangle counts, high level measures of a graph in the social network graphs. The graphs can also count triangles in a graph, which basically will tell about the cohesiveness properties exist within a particular scenario. And also it can apply, we can apply the PageRank algorithm to the graph to find out the ranking of the nodes. PageRank algorithm is also a well known algorithm which is given by the Google to find out the most relevant pages, web pages, which a user wants at a particular instance of time. So, for any search engine, this PageRank algorithm is a well known algorithm and is heavily used in the web graph. It can also join the graph together and transforms the graph quickly. We will see this particular aspect of the transformation and joining of a graph together to solve various problems in the further slides. It can also support the Pregel API that is given by the Google for traversing a graph. Now, we will also introduce here about how the vertices and edges of a graph, what are the different data models which are supported in the GraphX, which runs on top of the Spark core. So, as you know that Spark supports the data type which is called a resilient distributed data set, that is called RDDs. Now, this particular RDDs will use the vertex RDDs. So, that means the vertices of a graph are represented as resilient distributed vertex data sets, that is called vertex RDDs. Similarly, the edges of a graph are represented as the edge RDDs, that is the edge component of a graph, which is represented as the edge resilient distributed as data set. Together, these particular components, the vertex RDDs and edge RDDs, which are supported to construct a graph that is called a property graph in GraphX. So, graph is called property graph, which is nothing but the vertex RDD and edge RDD, which is supported as a graph in the GraphX. Also, there is another viewpoint wherein vertex and edges are combined together, that is called a triplet. The concept of triplet is very useful in building these graph algorithms which we have discussed, like PageRank algorithm, connectedness, and finding out the triangle counts, degree distribution, and the connected components. Which are some of the important graph algorithms. Such as the PageRank algorithm, then connected components algorithm, and then triangle counting algorithm, and degree distribution, average path length. And for graph traversal algorithms, which are going to be very much useful. Single source, shortest path, and so on. There are various graph algorithms which we are going to see, and these graph algorithms are iterative in nature. Therefore, the support of the graph that is called a property graph and the triplets, that we will see how this GraphX will provide the important basic features, and also the libraries of GraphX which support all these algorithms in an optimized manner. Now, graphs are also used in the machine learning landscape. For example, the models and dependencies of the data which can be represented in a form of a graph, whether it can be a small or a dense graph, or it's a sparse graph. So that means once a data is represented in a form of a graph, then machine learning can be applied on this particular graph as a data. These particular aspects we will discuss more details in this part of the course. So what do we mean by the parameter server? That means when we going to deal with the programming of the machine learning using graph, we will basically encounter with the large and dense graph which has to be dealt with the parameter servers. Similarly, the operations which are there in the machine learning algorithms which are implemented on top of the data sets which are represented as a graph has to be done in a graph parallel and data parallel operations, that we will see how we are going to support these architectures. Similarly, another architecture which is going to be supported for the big data landscape and which is there in the machine learning landscape is about the MapReduce application on small and dense scenarios of a big data. So the basic architecture which we will discuss here is the GraphX, how this GraphX will be supported as the framework which can also build the machine learning landscape. Similarly, all these part we will discuss in this part of the lecture. So graphs are there everywhere. So graphs are structured data which is there everywhere. Let us take some examples where you can understand that the importance of a graph computation is very much required in today's workloads. So for example, social network which is visualized as a social network graph. In this social network graph, the people are called as the nodes. So these are the people, they are called the nodes of a graph, and the relationship between these people, they represents the edge. So hence the graph comprises of the nodes and the edges of a social network graph, where the nodes represents the people or the users, and the social relationship is represented by the edge. Similarly, the people who does the posts, and they also performs the like operation, is also can be represented in a form of a graph that represents the post as the nodes and the likes is basically the relationship as an edge. So the graph data or a social network data you can represent in a different form of graphs and further do the analysis on top of it, that we will discuss. So graphs are a structured data, and it's there everywhere. Another such example of the graphs is about the web graphs. So for example, the Wikipedia has 1000 different climate change pages. So if we represent the Wikipedia as a graph, as a web graph, then we can find out that all the web pages will become the vertices, and the links are among these web pages, they becomes the edges. Hence this will form the web graph. So we can see here these are the web pages, global warming and climate change and so on, they becomes the vertices, and the connections between or the links between these edges or the web pages, the links of the web pages becomes an edge, and these web pages is the nodes. So this will form a web graph which comprises of the nodes and edges. Similarly, another form of web graph is the political block data. So that means the blocks which represents the political blocks is also represented in the form of a web graph, wherein the web pages are the vertices and the links are the edges. So the graph which is formed out of these web pages and the links are called as the political block graphs. They are also the web graphs. Similarly, the Bitcoin transaction network also can be represented in a form of a transaction graph or a transaction network graph. Wherein the vertices represents the people and the organizations which are executing the transactions of the Bitcoin, and the edges are representing the interactions or exchange of currency. Therefore, this kind of interactions between the people and exchange of currency, they can be captured in the form of a graph, and is called the transaction network, Bitcoin transaction network graph. Similarly, another kind of graph is there in the internet communication network, can also be represented in a form of a communication network graph, wherein the vertices are nothing but the routers and the internet devices, and the edges are the network interactions or the flows of the data between these devices is represented as an edge. Therefore, the communication network can be modeled in a form of a graph. Communication network graph, where the nodes are or the vertices are the routers and various internet devices, and the connections between them that is also to be taken as the network flows is becoming an edge, and this becomes a graph. Similarly, to detect the frauds among for the companies, so for example, Enron email graph can also be built up, can be used. So Enron was the company which has committed fraud. So their email exchanges between different users is modeled in the form of a graph for this kind of analysis. So here the users will become the vertices and the email exchanges are basically the edges. So this will form the Enron email graph, wherein the vertices are the users who have exchanged the mails, and these edges are the set of users who have communicated through the mail. Similarly, the user item graph can also be visualized as a bipartite graph, wherein the vertices are the users and items and their ratings. That means the users will give the rating to the items or the products. That becomes an edge with the weights given as the ratings. So bipartite graph, user item graph, is a bipartite graph where the vertices are the users and items, whereas the edges are the ratings given by the user for different products, can be represented in a form of a graph. Now let us see some of the analytics which can be performed on the graph. So graphs are central to the analytics also. Let us consider the raw Wikipedia corpus, and using this raw Wikipedia corpus, we can construct a table that is called a text table, which has the title and the body within it. Using this particular text table, we can construct an hyperlink graph. On hyperlink graph, we can run the PageRank algorithm, and after this PageRank algorithm, we can find out the top 20 different pages. So their title and their page ranks are extracted in a form of a particular table. Now similarly, from a text table, we can construct another graph which is called a term document graph, and this particular term document graph, we can apply a topic model algorithm, and from that we can extract the word topic table, that is word and topic table on top of it. Similarly, from the raw Wikipedia, again we can construct another table which is called a discussion table, wherein the users and discussion topics are mentioned. From this we can generate an editor graph, and we can apply a community detection algorithm on top of it. So we can identify the user community, users and different communities which are there in the raw Wikipedia text. Now we can combine both of them, that is the topic model and the user community together to get the topic community information in the form of a table. So these, from raw Wikipedia, we can get top 20 pages with the title and their page ranks. Similarly, from the raw Wikipedia text, we can get the word and their topics corresponding. Similarly, from raw Wikipedia, we can get the topics and the different communities. So this is basically the start point of analytics, and this flow or the sequence in which we can get this particular output or the analysis out of that text is basically called a pipeline. So, we will see here in GraphX that not only it provides the analytics which can be performed on the raw text or in raw data, and these the steps or the stages to transform the data from raw Wikipedia into the output of that is top 20 pages and extract this insight from the data is called the analytics. So, the graphs are also used in the analytics, and this support of making the pipeline, building the pipeline and performing the analytics is also supported in the GraphX that we will see in this discussion. Now, we will see the PageRank, which is very central to the graph analytics. So, here we can understand that this PageRank algorithm is a parallel computation algorithm, and it also performs in different iterations that also has to be done in a parallel, and these iterations will continue until it converges, and every iteration has to calculate the weighted sum of neighbors rank and do the summation and find out with a new page rank, and this kind of page ranks are updated. This update of the page rank continues over several iterations till it converges, and then only this page rank algorithm will finish its operations. So, let us take the internal important operation which is required to be supported to run the PageRank algorithm efficiently is that. So, first the neighbors or a neighbor pages, neighbor nodes which represent the pages, they send their data. Rather, we can say that if you want to find out the page rank of the node A, so it collects or it gathers the page rank information from the neighboring node. After gathering it, it will then compute its update, then it will update its page rank. And then it will again disseminate and then it will disseminate the same information again, that is called scatter. So, all these three steps, gather, apply and scatter, is treated as the super step, that is, it will be treated as one single operation, and if it is supported, then writing the page rank algorithm will be quite easier and also will become very efficient. So, these kind of constructs are being provided in the GraphX that we will see, and using these constructs, the GraphX also provides the PageRank algorithm as its library functions. So, all the library functions which are provided as the graph algorithms in GraphX are highly efficient and optimized in this particular scenario. Similarly, we can also see that shortest path algorithm also exists as the library in the library of GraphX, is also using this gather, apply and scatter paradigm, and using this in parallel at all the nodes, this particular function will be performed. Hence, data parallel and computation parallel operations are being done to support these algorithms. Another algorithm is to find the triangles, is to count the triangles, and in this manner we have to measure, we can measure the cohesiveness within that community. So, this particular way by counting the triangles, so here we can see that, so as far as this node is concerned, 1, it has 1, 2, 3, 4 triangles which are passing through this node 1. Hence, this particular node is a part of a large number of community. Hence, this particular node gives the cohesiveness. Compared to the node, compared to the other nodes which are not that cohesive. So we can count. So this particular node has only the vicinity of one triangle, which passes through only one triangle. So this particular node, which is shown over here, is more cohesive compared to the other nodes. So here we are going to analyze these particular behaviors in any community which we are going to deal with that. So counting triangles is one of the important algorithm which is supported as far as the GraphX libraries that we will see. So now the graph parallel operations, we will see the pattern how that is all supported. So consider this particular graph, and we are going to take this particular node, and we have to run the algorithm on this node. So if we can run this algorithm on this node, we can run in parallel at all other nodes. So let us understand how this particular algorithm we can design. So computation in most of the graph algorithm depends upon the neighbor node. So it will gather the information from the neighbor node, perform the computation, gather, apply, perform the computation, and then scatter this information which is being computed for updation at all the ends. So this kind of operation is in parallel being run at all the nodes. Hence, this graph parallel computation can be performed in this particular manner. Therefore, the graph parallel pattern is a part of GraphX implementation. So let us see the graph parallel pattern is supported by a gather, apply, and scatter notion. Using this, many graph parallel algorithms are now available with the GraphX libraries. Some of them are performing the graph analytics, as we have told that PageRank algorithm is there, shortest path, graph coloring. All these algorithms are available which uses this graph parallel framework. For community detection, triangle counting, K-core decomposition, K-truss, all these algorithms are available. Similarly, for machine learning, we have graph SSL and co-EM algorithms available. Similarly, for collaborative filtering, alternating least square ALS algorithm is also there, and stochastic gradient descent, tensor factorization. These algorithms are using the graph parallel approach for building. So graph parallel systems are available as on date is given by the Google, that is in the form of Pregel APIs, that is called a Pregel. Another graph system which is called Apache Giraffe, and another one is called GraphLab. And we will see that GraphX is performing better in all these scenarios. So we will expose different APIs to simplify the graph computation, and that is the graph parallel computation systems. Now let us see that how the Pregel gives an abstraction, and so that the graph computation becomes quite easy and for the programmer, and rest of the intricacies are hidden into the framework of. So in the Pregel, it will be vertex centric operations. So that means you have to think like a vertex, and it does not require MapReduce to be introduced here in the program. So only vertex centric computations or program can be written by the programmer. Hence it becomes very easy to write the graph algorithms using Pregel. Now, vertex programs will interact by sending the messages. So, let us see here in this typical example that, so if we are going to write down for this particular vertex I the PageRank algorithm in Pregel, so it will perform this particular PageRank on this particular node I by sending different messages. So, first it will receive the messages from its neighbor, and then it will does the aggregation of it, and after that then it will compute or it will update the rank, that is called the apply operation, and then it will scatter these two different nodes. So, this particular paradigm is being applied at all the vertices in parallel. So, only one vertex program we have to write down, the rest of the algorithm is taken care. So, writing the algorithm, graph algorithm using Pregel becomes quite easy without bothering about much intricacies. Similarly, in a GraphLab, there will be a pull abstraction. So, same algorithm of PageRank, if we can write down in a GraphLab using pull abstraction, so it will become a vertex program directly access the adjacent vertices and edges. So, GraphLab PageRank for the node I can also be seen as it will now compute the sum over the neighbors using this particular iterations, and that means it will collect the information, compute the compute the page ranks out of the neighboring pages information using this particular formula, and then it will update its page rank, and that's all. So, here the data movement is managed by the system and automatically it will be handled. So, the user has to write down for these vertex programs, and rest of all it will be taken care. So, that means when these data from the neighbors are required in the programming construct, automatically the pull abstraction will get these values from the neighboring node, and that is the part of internal parts of the GraphLab. Now, in short, what we have seen, these graph frameworks, they provide the features in which you can communicate with the neighboring nodes, neighboring vertices, and after the communication is reached, is being obtained or is reached from all the neighbors, then there will be a barrier, and then the computation will be performed, and then it will then again communicate. So, this is the paradigm which is called an iterative bulk synchronous execution, which will provide the parallel graph computations. So, this particular diagram shows the BSP, a bulk synchronous execution of the graph computations. So, this you can understand that when you say communicate, you can gather, and when you compute, then you say gather apply, and again when you communicate, it will become I scatter. So, again I told you that all these operations are have different names and paradigms in different the graph frameworks. Let us say Pregel, and then the GraphLab and Giraffe and GraphX. So, all these are performing the same set of basic operations to support the iterative bulk synchronous execution, and using that the vertex programs can be written in a very simplified manner for different graph algorithms. This we have already seen that using Pregel or using Giraffe or using GraphLab, it will expose the specialized APIs to simplify the graph programming and exploit the graph structure to achieve orders of magnitude performance gain over the more general data parallel systems. So, for example, the page rank on live journal graph, if you see that if it is done through the Hadoop, it is taking 1340 of this particular time, compared to the naive Spark. If you use, it will take 340, 354, and GraphLab is 22. And even the this one, even if you see the GraphX, which is even faster than the GraphLab also. So we have seen how this particular improvement in the performance is gained is because these basic operations and the algorithm are optimized and being supported by the core Spark and optimized by the GraphX for this algorithm. So those algorithms which are part of the libraries of GraphX are much more efficient in the performance wise compared to any other framework. Similarly, the triangle counting, and if we see that it is 1000 times faster in GraphX. Let us see this we have seen. Now, so basically now we have to go and see how these graph systems are being supported for their implementation. Now, as far as these data, we have seen that the data can be easily represented in a form of a table, and that particular view is called a table view, and the computation can be easily performed on this view that is called table view to get the results. Similarly, there is another view that from this table view we can get we can convert in the form of a graph. So it will become a graph view, and then various algorithms can be applied with the help of Pregel APIs, GraphLab and Giraffe. So this particular graph will be useful for applying different graph algorithms to get the results back. So we will see that there will be two different views. From table view we are converting to graph view, and then again into a table view. So there is dependencies between table view and a graph view. Let us see how the different framework they are handling this kind of views. So having separate views for each view is difficult to use and also will become inefficient. So why? Because the data will be moving and also there will be a duplication into the network and the file system. Therefore, this particular changing of views from table view to the graph view and again back to the table view requires the data to be moved through the SDFS file system. Hence, it will become inefficient in most of the scenarios. Now, as far as the GraphX, why we are understanding about GraphX is that it will give a unified approach and it will not incur these inefficiencies of internal or basically the use of file system and the network to store the data in between. Hence, it is called a unified view. So GraphX provides a unified approach wherein the data will not be required to store in SDFS. So between different views automatically they are being integrated together and data can remain in memory. So all the operations are supported with full efficiencies. So therefore, this new APIs which are supported in the form of the GraphX will blur the distinction between the tables and the graph. So the new system which will now evolve in the form of a GraphX as the unified approach will combine the data parallel and graph parallel systems together. So this will enable the users to easily and efficiently express the entire graph analytics pipeline that we are going to see. So therefore, the graphs and the tables are composable views of the same physical data, and this GraphX will provide a unified representation. So each view has its own operators that exploit the semantics of the view to achieve the efficient execution. So table and the graph, both views are together unified and is being supported in the GraphX. So therefore data parallel and the graph parallel operations are integrated together and is being supported as unified view for better efficiency. Graphs can also be represented or mapped in the form of a relational algebra, and therefore we can encode the graph as distributed tables and express the graph computation in the relational algebra, recast the graph systems optimizations as distributed join optimization and incremental material maintenance.